And now I want to go over to still something in this context, namely to the question what happens. I mean, I want now to change the covariance matrix a little bit by adding maybe one particular eigenvalue. So I mean, this is the situation where my covariance, the covariance between the entries of my vector is identically, which means all of them are independent, but they have also all the same strengths. They all have variance 1. Okay, and I mean, I can change now, not changing half of them to 1 and half of them to 2, but say I only change one of them to something which is different from 1. And the idea is that this here is somehow background noise, and there is one eigenvalue which carries information. And the question is, can I see this information somehow if I measure the distribution of the Wishart matrices? That's what I want to address in the following, and that's, I mean, such models are called spiked models or random plus noise, signal plus noise. And yeah, so we want to see whether we can understand this. And you already had, I think, some assignments where you looked numerically on this, where you saw that really you can see something. But now we want to check whether we can understand this also from a theoretical perspective. So this will be a small chapter, next chapter on those models, which very often go under the name of spiked models or signal plus noise. And the question is, can you see the signal in the noise? I mean, that's what you usually want to see in statistics or observations. So there's a lot of noise around, but there is some signal hidden there, but can you really get the information about the signal somehow out of your measurements? Okay, and this means in our setting, so we are still looking on our Wishart matrices, but now I'm changing the covariance a little bit by adding 1 degree of signal, let's say. So consider the covariance of the form. So my sigma, that's the covariance of my random vector. My random vector is in R to the P, and so the covariance between them is the identity matrix, but now I'm adding a deformation into one direction. So mu is a number, positive number, and u is an eigenvector. That's the eigenvalue. That's the eigenvector corresponding to this direction, 1 plus mu. So in this direction, I have 1 plus mu. Okay, and that's the idea. In this is an eigenvector which contains some information. Okay, so this here, let's say this corresponds to the noise. I mean, this is just background, which is uniformly distributed in all directions with, okay, normalized to strength 1 here. But then this here is a kind of signal, some information, which has strength mu, or actually 1 plus mu, and it goes in direction u. So u is a vector in R to the P, which is the eigenvector corresponding to this. So u, let's say I normalize it to 1. So u times ut is a P times T matrix. So I'm multiplying a column vector with a row vector, and this gives a matrix. So in the usual way. So this is a rank 1 matrix. So u times ut is a rank 1, and actually, I mean, it's a rank 1 deformation of this guy here. So P is big, so in a sense, this is a small deformation of the identity matrix. Okay, so it's a rank 1 deformation of the identity matrix. Yeah, okay, and now the question is, if I now look on the Wishart matrix corresponding to this, what do I see in a spectrum? Do I see this guy here somehow? Or for which mu do I see it? How, I mean, if mu is very big, I expect I should be able to see it, but how big has it to be, and is it really there? And can I really see where it is sitting? Okay, so I'm looking on my Wishart matrix, which is as before, I mean the sum xk transpose k from 1 up to n, where the xi's or the xk's have a distribution with this covariance matrix. Okay, and they are independent copies of this. So I'm making n observations of this situation, which is given by this distribution. And the question is, what are the eigenvalues of this guy? So that's what I can measure, the eigenvalues of this Wishart matrix. So this is now the Wishart matrix, not for the identity covariance, but for the one which is deformed by this guy. And the question is, what are the eigenvalues there? Okay, and I mean, is there anything to see? And of course, if I'm thinking about the asymptotic eigenvalue distribution, this guy doesn't play a role. So I mean, it is a finer kind of question. It's somehow a deformation about the asymptotic limit. Good. Okay, but let us think about how the situation should look like. So maybe let me write here is sigma, the covariance matrix, and maybe here I'm writing down our Wishart matrix. And so Marchenko-Pastur, that was the situation when the covariance matrix was the identity matrix. So this only had eigenvalues, all of them equal to 1. Okay, and then, I mean, in sigma hat, we are not seeing this peak at 1, but we see this smeared form of the Marchenko-Pastur distribution. So that's what we calculated. So Marchenko-Pastur somehow, I mean, it goes from gamma minus to gamma plus, and it has some distribution there, which we can calculate. And this corresponds to the situation, corresponding to this. Okay. And if we do an observation, I mean, we saw at least in our simulations, and we also know from concentration that if I measure the eigenvalues of sigma hat, of course, I mean, I have a matrix which is n by n, not infinity large, but I'm close to the asymptotic limit. I'm very close to this picture in the sense that I only see eigenvalues where they really should be. So in particular, if I'm in this situation, the largest eigenvalue is really very close to this at this point. I don't see eigenvalues somewhere sitting here. And that's very important, because this means if I see something outside here, then this means I must have a deformation there. Okay, so I mean that's an important point for our random matrices, those kind of concentrations, that the concentrations are very strong and we don't really have big fluctuations of the eigenvalues. So if we do an observation, we really see that the eigenvalues are more or less distributed according to this picture, and they are sitting very, very close to the place where this picture predicts that they should are. So in particular, there are no outliers somewhere here or here. So okay, and so now this gives us the hope that if I have here an additional eigenvalue, then this might be visible somewhere here, and because we know it cannot really come from the bulk here, this must correspond somehow to the outlier which we have there. And we saw this in simulation. So namely, if I now look on the situation which I have here, so I mean I still have all but one of the eigenvalues are sitting of the eigenvalues of sigma are at 1, and then I have one eigenvalue, so tiny one, at 1 plus mu. So that's the situation which I consider there. That's sigma, and then what do we expect to see here, or what did we see in our simulations? That actually, I mean, we still have, essentially we have this bulk here corresponding to all the eigenvalues from here. So that's still this one. But then, at least if mu is big enough, we really see shadow of this guy somewhere popping up here. So we see one additional eigenvalue here, which sits at one place, lambda. But this lambda doesn't have to be this 1 plus mu. It's at some place, and we are trying to understand what the relation will be. But at least that's what we expect and what we already saw. So there is one eigenvalue here. So there are many eigenvalues which are distributed according to Marchenko-Pastur, but one eigenvalue pops out, and this must be coming somehow from from this deformation here. Okay, and because of this concentration, we know that eigenvalues which should sit here will never sit there. That's a concentration. So in particular, for the largest eigenvalue, we really know that the largest eigenvalue for Marchenko-Pastur is very close to this boundary here. I mean, we didn't prove this in full details, but I mean, in principle, with the concentration machinery which we had, we can prove things like this. So that's a very important point. The largest eigenvalue of this guy here is never moving out far away. So it's exponentially close to this guy here in n. So this means if you see something here, it cannot be a fluctuate. It cannot come from the largest eigenvalue from here, but it must be something else. Okay, and so the question is, can we theoretically understand this? And in particular, can we also understand where this guy here is sitting at the position lambda if we have here a deformation by the strength mu? So what is the relation between mu and lambda? That's what we want to understand. Good. Okay. And maybe I give you right away the theorem. So there's a precise statement about this. There's a precise relation between mu and lambda. So let me give the statement and look a little bit at it. And then so it's one vector. But I mean I'm only asking here about the eigenvalues. Of course, the second question is so this guy here, this will have a specific eigenvector, and this eigenvector, of course, should remember somehow this u. It should also be close to u. I mean, if I'm looking on the eigenvectors for those guys here, they don't contain information. Of course, the information there is the strength, but maybe the u is even more important because this tells me what are the important features of my signal. Okay, and so there is also a statement telling me that if I really see this guy, then the eigenvector of this has a substantial overlap with the eigenvector u. But that's not what I'm going to formulate now. But you can also see this. And then if you don't see this, then maybe there is an eigenvector corresponding to this, but then all information is lost. Okay, so if you see this guy here, then you also can look on its eigenvector, and this will give you information about the eigenvector u from your signal. Good. Okay, but I only talk about the eigenvalues. Okay, so consider. So let me fix the mu bigger than 0. And I consider the covariance matrix as before. So this is this identity matrix, and then it's this perturbation with mu in the direction ut. And then what I want to understand is somehow the largest eigenvalue of sigma hat. I mean, that is the largest eigenvalue if something pops out here. And the question is, where is this sitting? And when is it? When do I see one which is different from the end of the Marchenko-Pastur distribution? Okay, so then the largest eigenvalue, let me call it lambda, of this Wishart matrix, sigma hat, is, and of course, in the asymptotic regime where n is very large and p is also very large, such that the ratio is gamma. So this is in the asymptotic regime, where p and n both go to infinity, but in such a way that the ratio of them goes to gamma. And again, let's say gamma I'm fixing in this interval 0 to 1, but I can, it's the same statement if it is outside, but anyhow, so it's given by, this lambda. Okay, so I really see something if the mu is actually bigger than the square root of gamma. So I mean, mu has to be big enough, and how big? It's really the square root of gamma which determines this. And then I see here something which is sitting at 1 plus mu plus gamma 1 plus mu divided by mu. Okay, and if mu is not big enough, then the signal is not strong enough and I won't see it. And then the largest eigenvalue is just this largest eigenvalue coming from the Marchenko-Pastur distribution, which is sitting at gamma plus. And then it is at gamma plus, which was 1 plus the square root of gamma squared. Yeah. Okay, and maybe one should note that if mu is bigger than this, then this quantity here is really bigger than this. So this is really an eigenvalue which is sticking out, which is bigger than the endpoint of the Marchenko-Pastur. And if mu is approaching this, then actually this is going to this. So maybe if I put mu equal to the square root of gamma, so if mu is equal to the square root of gamma, then what I get here, this is 1 plus square root of gamma plus gamma times 1 plus square root of gamma divided by square root of gamma. And so you see I have, so this is just square root of gamma. So I have 1 plus square root of gamma times 1 plus square root of gamma, which is exactly gamma plus. So this here is a kind of continuous transition. If I'm bigger than this, I have this quantity, but if I go down to the square root of gamma, I actually approach this. So this really means the mu, if I make the mu big enough, I will have a lambda there. But then if at some point the mu is square root of gamma, this is exactly the point where this has moved to the bulk here, and then if I'm making the mu smaller, I won't see it anymore. Then it just disappeared in a bulk. And then I cannot see it, this effect of the signal anymore. Okay, good. Yeah, and maybe those results, they maybe, let me say a few names. Bike and Sylvester did more or less version of this. And then maybe there's also work of Bike, Benarous, and Péchet, who also looked on fluctuations and many stuff in this context. And so all of this is around 2005 or 2006. And usually this kind of transition is called, according to this paper, BBP transition. So Bike, Benarous, and Péchet. BBP transition. Where you have this transition between the behavior that you see, this thing here, and if it's getting smaller, it will disappear. So you have a transition between just seeing the bulk, and then suddenly you see something extra. And you can also describe the fluctuations of this. Okay. But you should notice that we cannot make an asymptotic eigenvalue statement. I mean, if I'm seeing something like this, so this I have the bulk here, and then I have one eigenvalue sitting here. If n goes to infinity, then of course, as the eigenvalue distribution, this guy here will disappear, because it is just weighted with 1 over n, or 1 over p. Those are p by p matrices. Okay, so I have here p eigenvalues. P minus 1 are sitting here, and 1 is sitting here, but in the asymptotic regime, this here converges to something where I don't see this. So I cannot formulate the result by saying that I have an asymptotic eigenvalue distribution of this situation, because then this individual one eigenvalue, you cannot see it in the limit. Okay, so it's really the statement that if n is very large, you see one eigenvalue sitting at a specific position. So we have to mix somehow asymptotic knowledge with knowledge about what happens for very large n. Good. Okay, so and maybe let me draw here maybe this picture just to have a few concrete numbers. I mean, you should have seen those maybe in your histograms, but maybe let me do this again. So here I have so maybe let me look on the situation gamma is equal to 1, where really my matrix X is a square matrix, which means n is equal to p. I make as many observations as the dimension of my vector p is. So for gamma equal to 1, just to have here concrete numbers. Yeah, I mean for gamma equal to 1, the Marchenko-Pastur has a singularity at 0, and then it goes down at gamma plus, and gamma plus in this case is equal to 4. So it's 1 plus the square root of 1 squared. So it's 2 squared. So it's equal to 4. This is what we see if here my peak is sitting at 1. Yeah. Okay. And then what is the boundary? So if gamma is equal to 1, then mu equal to 1 is where I really make the transition. Okay. And if mu is equal to 1, which means here the 1 plus mu, which is the eigenvalue corresponding to this u. So this is at 2. This is the situation where actually somehow this guy here goes here at this position, but it will not be visible. So it's the same as the largest eigenvalue of what I had before. So here, if I have this strength, then that's the point where I start to see things. And then maybe if I take here 3 or 4, then maybe for 3 I'm going to 5, 1/3. So this guy here will appear here as such an eigenvalue, and 4 appears here as 6/1/4. So you see, I mean, I'm not seeing exactly the same value here, but of course I have a very precise relation between them. Okay, and I mean, this 2 here, I mean, it doesn't have to be bigger than the 4 here. I mean, if I'm going here up to 2, then I start to see something. So I mean, here I have some smeared out things. This is the smeared out stuff corresponding to the eigen values 1. But I mean, I don't have to move here out of the 4 so that I see something, but I will start to see something earlier, namely starting here at 2. So it's a nice thing. Maybe it's clear that you expect something like this, but this precise relation probably is not clear at all. How do you get this? Okay, and so maybe that's what I want to do in the following, namely to see how can we really understand this relation. How can we calculate this largest eigenvalue in sigma hat? And in this case, we really try to calculate our eigenvalue by looking on the characteristic equation. I mean, that's the thing which we didn't do when we looked on Marchenko-Pastur. Because for Marchenko-Pastur, you could say, okay, I have a matrix. I want to calculate its eigenvalue. I just write down that the determinant of A minus lambda is equal to 0. But of course, my matrix is very big, and you cannot get directly information from this. But now, if I make a deformation by a rank 1 thing, then actually we will see that this is a good way to go if I'm outside of the bulk where I see Marchenko-Pastur. Because then I can reduce somehow this p-dimensional determinant to one-dimensional in one way. Okay, which is not clear now, but so we really have to do it. So it's a nice combination of small little algebraic tricks and calculations. And maybe I should also say, I mean, what those people also did was that you are not only looking on a rank 1 deformation, but maybe a rank 2 or rank 3. So maybe you have a finite number of spikes. You're not just adding one outlier, but you add several to them, and then you expect that you see a corresponding number in the spectrum of the Wishart matrix. And you can also describe this. Okay, but the one-dimensional case is maybe simpler, so I will stick to this, because then the calculations are easier. Okay, and so for this, I mean, what I want to do, I want to calculate the eigenvalue distribution for this deformation of the ordinary Marchenko-Pastur law. And so what I want to do is, of course, I try to connect this deformed thing with the Wishart matrix which I had before. Okay, so I mean, we write the sigma hat. So the sigma hat, of course, is 1 over n x transpose. And now this x is my data matrix where I have vectors which have a covariance, which is the identity plus this rank 1 deformation. And of course, I can transform, I can transform any Gaussian vector with any given covariance to a vector where I have the identity covariance by multiplying the thing with the square root of the covariance matrix. Because we know how under linear transformations the Gaussian vectors change. Essentially, the covariance changes with the conjugation of the matrix with which I multiplied. So I can write this here as as 1 over n, and then I write this x as sigma to the 1/2 y transpose sigma to the 1/2. So I'm writing my x, which has the covariance matrix, which is identity plus this deformation. I write this as sigma to the 1/2 y. So the sigma, the sigma is essentially a diagonal matrix where I have everywhere a 1, and at one place I have a 1 plus mu. Okay, and now if I want to transform a vector which has everywhere variance 1, I just multiply it with this diagonal matrix, so that for one of the arguments I'm changing the variance from 1 to 1 plus mu. Okay, so this is just a simple transformation. And this y, this is now our good old ordinary Wishart matrix corresponding to the covariance identity, which has the Marchenko-Pastur distribution. Good. Okay. So the y corresponds to Marchenko-Pastur. So this means this here divided by 1 over n. This is really the matrix which has Marchenko-Pastur. Okay. And now I want to look. I'm looking at eigenvalues of this matrix. So I want to have an eigenvalue lambda, which should be outside of the part where I have the eigenvalues of Marchenko-Pastur. So we are looking for an eigenvalue, which I call lambda of this guy. This will have many eigenvalues which should be similar, which should be like the Marchenko-Pastur. But then I'm looking for the one special one, which should be outside of the interval of the Marchenko-Pastur. So I'm looking for an eigenvalue lambda of this one, which is outside of the interval from gamma minus to gamma plus. But that's where the eigenvalues of Marchenko-Pastur are sitting. So I want one which is bigger than gamma plus. And I want to check, can I somehow calculate one out of this? Okay, and now I'm really doing this by looking on the determinant, the characteristic equation. So this is an eigenvalue. So this means it should satisfy that 0 is the determinant of, okay, my matrix is 1 over n. So it's this guy here. X transpose minus lambda times the identity matrix. That's the equation for, that's the equation for all eigenvalues of this guy. And of course, I cannot really solve this equation in any way in general, but I'm looking for a special one. Okay, and the idea is that, of course, this X is now the deformed guy, but I can relate it with the undeformed Wishart matrices by going over to y. So that's, of course, the first thing I want to do. I want to rewrite this in terms of y, because there I know precisely where the eigenvalues are sitting. So I should take out this covariance matrix. So I'm writing this as the determinant. And this x, I have here this sigma to the 1/2 and here the sigma to the 1/2, so I can split it off. So I'm writing this as sigma to the 1/2 times 1 over n y transpose minus, okay, and then I'm splitting also off on the other side the sigma to the 1/2. So that is, of course, what I get here. But then for the identity, of course, I have made a mistake. So I should repair this by putting here the sigma, the lambda, times sigma to the minus 1. So essentially, I have moved the sigma from here to here. But this is now the quantity of which I know the eigenvalues. So this will be helpful. Good. Okay. And then, of course, the determinant of a product is the product of the determinants. So it will be the determinant of this times this, which is the same as the determinant of sigma, and then it's a determinant of this thing here. Yeah. Okay, but now the determinant of sigma, I mean, so I have now here product, and I want to see when is it is 0, and of course I have written it as a product of a few things. The determinant of sigma, I mean sigma, so let me write again. So sigma is the identity plus mu times u transpose. Okay, and this is a matrix which is invertible, or which doesn't have eigenvalue 0. So this means the determinant of this is never 0. That's not a problem. So if I have the 0 here, then it must come from here. So this means what I'm looking for is actually a lambda such that the determinant of this guy here is equal to 0. So our equation for the lambda is that the determinant of, so I can forget about this because the determinant of this will not be 0. So the determinant of this has to be equal to 0. And so this is 1 over n y transpose minus lambda. And here I have sigma to the minus 1. This has to be equal to 0. And now you see I'm back. So this is my Marchenko-Pastur-Wishart matrix. And now I'm looking now for a kind of eigenvalue which also contains this one. So the question is, can we do something with this? Okay, and in general, I mean, for general sigma, this would be hopeless. But I mean, sigma is here just a rank 1 deformation of the identity matrix. And actually, for rank 1 deformations of matrices, we had a nice formula. This was this Sherman-Morrison formula, which a formula for the inverse of such a thing. That's exactly what I want here, and I have even here just the deformation of the identity. There we had it for general A. So A plus a rank 1 deformation, the inverse of this was the inverse of A plus something. And so if we do apply this here, the sigma to the minus 1, so this is the identity plus my rank 1 deformation. This was by this Sherman-Morrison formula. This was the inverse of A, but the inverse of the identity is just the identity. And then I had a rank 1 deformation, which also involved the inverse of this guy, but these are just identities, so this becomes very simple here. So it was minus mu times u transpose divided by 1 plus mu u transpose u. So this was this Sherman-Morrison formula applied to this specific situation. So you see it's essentially the inverse of the identity matrix, which is the identity matrix. And I have here a rank 1 deformation, u times ut, that's a matrix. And here I have utu. And utu, that's the inner product between u and u. But u is this was normalized to be a unit vector, so this is just 1. So this guy here, this is just equal to the norm of u squared, which we normalize to 1. Yeah, okay. But then this is very nice. So I can plug this in and see whether this helps us. So what I want is 0 should be the determinant of 1 over n y transpose. That's our ordinary Wishart matrix. And then I have minus lambda times this. So I have minus lambda times the identity matrix. And then minus, so plus lambda times mu times this u transpose divided by 1 plus mu. Good, and this should be equal to 0. And again, I should now use my information about Marchenko-Pastur. So I mean, because if so you see this here, I mean this part here, this is actually that is what you write down if you want to see whether lambda is an eigenvalue of this guy. And this we can control, and actually we are looking now for lambdas which are outside of the Marchenko-Pastur interval, which means we are looking for lambdas which are not eigenvalues of this guy here. I mean, at some point we have to use this information that actually we don't want the 0 coming from the fact that I have an eigenvalue from this guy, but it should just be coming from the deformation. And now I'm using this information because this is not an eigenvalue of Marchenko-Pastur. This means that this guy is invertible. And so I can essentially rewrite this here in the form determinant. Again, I take this guy out. So I write as 1 over n y transpose minus lambda I transpose. And I want to make a deformation with this. So I write this as the identity. So this is this term. Okay, but then this term, of course, I have made a mistake. If I want to take out this guy, I have to multiply it with this. So I have to take here plus, and I write this 1 over n y transpose minus lambda times I lambda times identity, and I have to write here the inverse times lambda mu u transpose divided by 1 plus mu. Okay, so it's a complicated way of writing this whole thing. But I want to separate out the effect which comes from the ordinary Marchenko-Pastur. That's this quantity here, so I take this out. And I can do this because I can invert this. If I would be in the spectrum of Marchenko-Pastur, then I might have problems with this. Or maybe the real problem would be that this actually determinant of this would be equal to 0. Because now again I have the determinant of a product, which is the product of the determinants. So it's the determinant of this guy times the determinant of this guy. But the determinant of this is not equal to 0. That's now really because lambda is, I'm looking for lambda, which is not an eigenvalue of the Marchenko-Pastur. So it's not an eigenvalue of this guy. So this is not equal to 0, which means my condition is now that the determinant of this guy is equal to 0. Okay, and here, okay, I mean, it still looks horrible, but we will do another small magic trick soon, and then it will become much simpler. Okay, so I mean, this guy here is invertible, so its determinant is different from 0, which means what we want for our lambda to be an eigenvalue outside of the domain of the Marchenko-Pastur is that 0 should be the determinant of this matrix here, which is the identity matrix plus, okay, and then I have lambda mu divided by 1 plus mu. Those are just numbers. Let me put them at the front. So it's lambda mu divided by 1 plus mu. And then I have this 1 over n y transpose minus lambda I p to the minus 1, and then I have u transpose. Okay. Yeah, and this is somehow the resolvent of my ordinary Marchenko-Pastur. Yeah, and now I mean, what we have here is still the determinant of a p times p matrix. So it's still a horrible thing. In principle, I mean, it has p eigenvalues, and we are looking on one of them, which has a specific properties. Yeah, but I mean, this here is a very specific form, so it's 1 plus, and here I have a product of 3 matrices. So this is a matrix, U is a matrix, okay, it's a vector, but a vector of course is also a matrix, and I have U transpose. And so what I have here, let me see, so this guy here, so this is of course, this is a P times P matrix. U is a vector, so it's a P times 1 matrix, and UT is the other way around. It's a 1 times P matrix. So this is a row vector. No, this is a column vector. This is a row vector, and this is a P times P matrix. Okay, and so I'm looking on this, and of course the whole thing here, this is a P times P matrix. Yeah. Okay, but now, I mean, there's this magic happens, but if I'm looking on traces or determinants, and I have things where I multiply matrices in one order, this is often related to the same kind of quantity if I do it in the other order. So instead of multiplying these three matrices in this order, I can also say, okay, I multiply this with this. This should be related to multiplying this with this. But if I multiply this with this, then I get a 1 times 1 matrix, which is just a number. And if this really is the case, then suddenly, instead of having a problem about a determinant of a p times p matrix, I have a problem about a determinant of a 1 times 1 matrix, which is just a number. And this is really the case. And so there's actually a general formula, which is Sylvester's determinant identity, which tells us that the determinant of identity plus a product of two things is the same as if I multiply the two things in the other order. Again, this is magic. It's totally trivial, but still it's magic and very powerful. So this is again one of the things, maybe even if you forget everything about what we have done here, just knowing about this or see that it is really useful is probably a good thing. So this is usually called Sylvester's determinant identity. Yeah, so what is this? So this is just about this. So I just consider two matrices. And the nice thing, this is about rectangular matrices. So let me take a matrix, which is a p times n matrix, and another matrix, which is a n times p matrix. So I can multiply those matrices in both orders. Okay, and then I'm saying that if I'm looking on the determinant of the identity plus AB, this is the same as the determinant of the identity plus BA. Okay, and now we should think, where are we? So if I multiply A with B, then I'm in P times P. So the identity here is the identity as a P times P matrix. On the other side, if I multiply B with A, then I'm have an n times n matrix, and here I'm in n. And I mean, what I have above, so the P is as above, and the n is equal to 1 above. So this means I have here a determinant of a P times P matrix connected or related, or actually it's equal to the determinant of a 1 by 1 matrix. And of course, the determinant of the 1 by 1 matrix is just the number there. So this means a horrible determinant, which I would suppose I have no chance of calculating it. Actually, it's very easy to calculate. Okay, and the proof of this is also quite easy if you know how to do it. So maybe let me also do the proof of this, because this is also a bit related to things which you are asked to do in the context of proving Wigner's semicircle law. And this relates with the Schur complement formula. Yeah, the point of seeing this is that actually you should see that those guys which I have here are ways of calculating the determinant of a matrix which contains both A and B. So A and B are rectangular matrices, and there are nice ways of putting rectangular matrices into bigger matrices so that you get a square matrix. And then in this bigger world, you can often do nice factorizations, and you can relate different factorizations, and this will lead to this here. Okay, so again, this is so philosophical that it doesn't mean anything until I really show you the concrete way of doing it. Yeah, so namely, so in order to see this, one should do the Schur complement formula. And this is essentially, I'm packing, I mean, I have two matrices A and B, but I put them into a bigger matrix, namely the one where I have, I put here, let's say, the identity, the P times, okay, so I'm taking a P plus N matrix, and I'm putting the A here and the B here. So I mean, this has size, so this here is size P, This here is size n, and here it is the same. This is so here it is P, and here it is n. So A is a P times n matrix, and B is a n times P matrix. So I can put them into such a matrix, and I have now a square matrix, a P plus n times P plus n matrix. And okay, in principle, I want to calculate the determinant of this matrix, and I can do factorizations. That's the nice thing. If I'm putting algebraic objects, which I have, into bigger matrices, very often I can do factorizations which are not there if you just do it on the base level. So namely here I can factorize this. So I mean I write it down, and then it's trivial to check it as a product of three things. So namely I put here 1, 1, B 0, 1, 0, 0, and now the non-trivial thing is that I have here 1 minus BA, and now you might see how this is related to what we want to do. And here I'm putting 1, 1, A, B. Okay, and of course those are the identity matrices, and I should check what is the size. So here I have P and N, P and N, P and N. Okay, and this is very trivial. You just have to multiply it. I mean, okay, you see that most things are just coming from a direct multiplication. So this 1 here you get from 1 times 1 times 1. There's no other way of, well, let me see, of getting it. This B here comes from B times 1 times 1, I think. And only this guy here, this is something where you have to sum things. So let me see, where do you get, so where does this here show up? So let me say this one here, you get by multiplying this times this times this. But then there's also another way of getting this, namely you get, so here you have to go from 1, 1, so you can go 1, okay, 1, 1, but then you can also, what can you also do? Here you want a 2, 2 entry, Okay, so with a 2, 2 entry, you can go, of course you can go 2, 2, 2, 2, 2, 2. So this is just multiplying this with this, but you can also go 2, 1. Okay, and then here you must go 1, 1, but then you can go 1, 2. So you multiply this times this times this. So you see from this you also get the product of B times A. And if you multiply this with this, then you also get minus B times A. So the B times A goes away. So this one, I mean, all those guys you have written in a trivial way. Only this one is written in a non-trivial way as 1 minus BA plus BA. This factorization does this non-trivial writing. Okay, I mean it's trivial. Just check it for yourself. Okay, so that's one way of writing this. But of course, I mean, A and B here are somehow symmetric. So you can also do a different factorization, which involves the A minus B. So you also can write this. This is more or less the similar thing as 1A 0, 1. And here you have 1 minus AB 0, 0, 1 times 1, 0, B 1. Again, simple to check. It's the same guy, and now only this one here is the non-trivial factorization. You get it as this times this times this plus this times this times this. Okay. So totally trivial factorizations, but now the magic is now I can calculate the determinant. I say I want to calculate the determinant of this. Of course, this is the determinant of this, and it's also the determinant of this. Okay, I have here a product of three things, but the first and the last term are always very special. They are triangular. And the determinant of such a matrix, you have here the ones, and you have here something, and then here a 0. The determinant of this is equal to 1. I mean, triangular matrices where you have ones on the diagonal, the determinant is equal to 1. So the determinant of this is equal to 1, and here, of course, something is wrong. Okay, here you should have a 0. This should also be triangular. Otherwise, of course, it wouldn't be helpful. Okay, you should check this factorization by yourself, that you believe it. It's trivial, but it it has to be checked. Good. Okay, so determinant of this is one, determinant of this is 1, which means the determinant of this is equal to the determinant of this. Okay, but on the other hand, it's also the same as the determinant of this. Determinant of this is 1, determinant of this is 1. So this means the determinant of this is equal to determinant of this, which is equal to the determinant of this. And now again, these are diagonal guys, so the determinant of this here, of course, is the determinant of this. The determinant of this is the determinant of this. And voila, that's the proof. Totally trivial, but nevertheless, it's kind of magic. I mean, if you are asked to come up with a proof of this, I mean, if you don't try it in the right way, it might not be so easy. Huh? If you do it like this, it's totally trivial. Good. Okay, but so let me see. So where are we? Yeah. Okay. So I think time is more or less over. So I mean, we are more or less done, but we have to put everything together, and maybe, yeah. Maybe I write down. So what we get from this is that actually, so what I have here is a determinant of 1 plus, and then I'm multiplying this matrix with this matrix, but by this Sylvester's formula here, this is the same as the determinant where I do it in the other order. So this means what I get here is that 0 should be the determinant of 1 plus, okay, and I have this, okay, these factors don't change, lambda mu, 1 plus mu, and now I multiply first the ut, and then I multiply with the rest, so I have here this thing to the minus 1, and then I have here the u. And now, of course, this here, this is just an inner product. This is the inner product between u, this applied to u. So this is just a number. So this determinant is just, I mean, this is a number, and this identity matrix here is really just the number 1. So this is now just that this quantity here has to be equal to 0. And you see, I have here the resolvent of something which is more or less the Stieltjes transform of my Marchenko-Pastur. Because I take the resolvent, I take here the inner product with a vector. So maybe one has to think a little bit about this, but in principle, what I have here is the Stieltjes transform of my Marchenko-Pastur at the point lambda. And then you see that I have here an equation which involves the Stieltjes transform of Marchenko-Pastur, but it gives me a relation between lambda and mu. Okay, and now one still has to think, I mean, this was a very complicated formula, so maybe it's not so clear that this gives us the nice result which I wrote down in the theorem here. But so maybe next time I will look on this. But so, I mean, the main calculation is now done, and the main ideas. Now it's just to try to understand that this is equal to 0, that this really leads to this. Good. Okay, so are there still questions on this? So I think it's a nice calculation, and it really, I mean, it's calculations with rectangular matrices still surprised me quite a bit. I mean, I've never worked with rectangular matrices. Usually my matrices are square matrices, but here this is surprising, astonishing. You have a product of 2 rectangular matrices. Okay, one knows it should be the same as if you do it the other way around in many cases, but that it really makes such simplifications from a p-dimensional problem, which you don't have any idea how to deal with it directly, to a one-dimensional problem, which is much simpler. Okay, and so maybe next time we see that we really now can solve this very easily. Okay, so that's it for today.